Hello, and welcome to Lecture 3, where we're going to begin covering Chapter 2, specifically sections 2.1 to 2.2, and cover the topics of position, displacement, and velocity. Okay? Our objectives are to distinguish between distance and displacement, apply the relationship between a particle's average velocity, displacement, and time interval, and distinguish between speed and velocity. Let's get some key terms out of the way. A particle is a very small thing, or just a simplification, maybe a time that we don't care about the details of a more complicated object. The term particle isn't going to be unique to these sections or chapter, but something we're going to see throughout the book, really. A particle is an object that can only translate in the x, y, z direction, okay? In other words, it cannot rotate because it does not have a defined size, okay? Because it is simply a particle. It's a single point in space, okay? Kinematics, that is the study of motion. Kinematics refers to displacement, velocity, and acceleration. So when someone talks about kinematics, that's what they're talking about. Displacement, velocity, and acceleration. In a poetic sense, it is the geometry of motion. It does not consider the cause of motion, which we'll soon learn is a force. Forces create motion. So kinematics just looks at the how, not the why of motion. But ultimately, it is the displacement, velocity, and acceleration. It's one of those three things. Now what about total distance? Well, what you care about is it's not the same as displacement. Total distance is the sum of the absolute values of all displacements. For example, a particle moves from x equals 0 to x equals 10, and then back from 10 to 0. Its displacement would be 0. We'll talk about exactly why. But its distance would be 20, because we just take 10 plus 10. Okay, well, now on to the formal definition of displacement. And it's quite simple. Displacement, represented as delta x, this is the Greek letter delta, is just final position minus initial position. So in the case of our example above with the t term total distance, the initial was 0, the final was 0, so our displacement would just be 0 minus 0 equals 0. Okay? Displacement is very easy to calculate, easier than distance even, which isn't very difficult itself. Average velocity, okay, represented by v, avg for average, can be represented as a v with a bar over it, is the change in displacement over the change in time. Or the change, is the displacement, not the change in displacement. It is the displacement over the change in time, which is just x2 minus x1 in the numerator and t2 minus t1 in the denominator. Okay? The units of velocity are meters per second, as you can see. Speed is, in this case, average speed is total distance over total time, elapsed time. Okay? The units would be the same, also meters per second. Okay? Well, what about instantaneous velocity? Well, instantaneous velocity is the notion, and this is not using calculus, but instead just conceptually the notion that as our elapsed time becomes smaller and smaller, we get a better approximation of instantaneous. And so if we can have that elapsed time become so small that it doesn't really exist, then we have the velocity at that particular instant in time. Okay? We won't, calculate it or anything, but we'll be given plenty of examples of instantaneous velocity. So let's look at three types of problems. I have one example of each. So type 1 are simple problems that involve something called a motion diagram. Type 2 are problems that involve a graph, such as the x versus time, or position versus time graph, an x versus t graph. And type 3 are problems that don't have a diagram or a graph, and instead have a word problem about velocity and require an interpretation of that word problem. All right, so here's type 1. This is what we mean by a motion diagram. A motion diagram shows the particular object at certain points in time in a pictorial sense. In this case, a dragster. So there's one point at P1 that corresponds to time 0 and position 19, and another point at time 4 and position 277. Okay, well, what's the question? Well, the question says, what are the average speed and average velocity of the dragster? Well, average velocity, of course, is just defined as displacement over the elapsed time. So that would just be 277 minus 19, because that's x2 minus x1. You can see x2 was 277, x1 was 19, and then t2 was 4 and t1 was 1. Good thing to catch there, right? Because you might think t1 is 0, but of course it's not here, it's 1. And that gives us 86 meters per second. What about the average speed? Well, the average speed is just total distance over elapsed time, which is the same darn thing. It's just 258, right? Because that is indeed the displacement, or in this case, also the total distance. So 86 meters per second again. Why do they agree? They agree because the dragster here didn't turn around. It continued on in the straight line. It never changed the sign of its direction. It never started going backwards. Okay? And then it says, or we're asked, is the car moving at constant velocity? Well, we haven't addressed that, but we can look at the diagram and get some more information. We can look at this segment here, the first second, because we know it started at 0, and then it made its way to 19 meters, but it took a whole second to do that. Well, that's a lot slower. That means that the average velocity in the first second was only 19 meters per second, as compared to the average velocity in the subsequent 3 seconds at a much greater 86 meters per second. That means it sped up. And if the average velocity changes, that means instantaneous velocity sure changes too. So that means definitely this is an example of a non-constant velocity situation. The dragster is not maintaining constant velocity. It's accelerating, but we'll define acceleration in the next lecture. Okay, example 2, a graph. Okay, so we're given a position versus time graph shown below. All right, and it's shown for 12 seconds of motion. The vertical axis is the dependent variable position. The horizontal axis is time, okay, the independent variable. The first question just requires us to read the graph. It wants us to know that wants for the position at 2, 6, and 10 seconds. Well, that's simply a matter of looking at 2, drawing a vertical line, finding where it intercepts the curve, drawing a horizontal line, and finding the value, which in that case is 10. So we just do that for each one, and we get 10, 20, and 40. And the line's already drawn on here for you. What is the object's velocity during the first 4 seconds of motion? Okay, so that would just be taking delta x over delta t. Well, the delta x is 20, the delta t is 4, so it's to be 20 over 4, right? Sure enough, 5 meters per second, which is the slope of this linear segment. And notice here that the instantaneous velocity is the same as the average velocity, because any tangent line along this graph would be exactly equal to the slope because it's linear. Okay? That only works when it's linear. Average being equal to instantaneous, that is. Second of all, what's the average velocity during the time frame of 4 to 6? Well, that's where the line is flat. That actually means that the displacement isn't changing, so yep, sure enough, that means an average velocity of 0. What about the velocity during, and again, here, average would agree if instantaneous for part C. For part D, again, average agreeing if instantaneous, but here we have a negative slope. Velocity does care about direction. Velocity is a vector. We talked about what a vector is, right? Vector has magnitude and direction. In this case, the direction would be backwards, okay? And so it's negative 20 divided by 2, or negative 10 meters per second. That's the velocity during the interval from 10 to 12. Okay, what about the average velocity from 0 to 12? Well, that would be from here to here. In this case, we draw a line to connect the two. Draw it a bit better. So draw a line to connect the two like that, okay? Now that isn't a tangent line of any part of the curve, but instead is a secant. It's just a straight line that connects 2 points. Well, we can just still use the definition of velocity, and we use 20 over 12. As a fraction, that's 5/3, or we round it to 1.7. Why am I using 2 significant figures? Well, I was being a little fast and loose with this problem. Again, I only do that with very simple problems like this one. All right, bonus question. What is the average speed from 0 to 12? So same time frame as in part E, but now I'm asking for average speed. Would it also just be 1.7? Do they agree again? Like the average speed and average velocity agreed up here, right? Well, no, definitely not, because the particle does start to go backwards. So that means that average speed actually would be the sum of the displacements, 20, 20, and 20, for a total distance of 60, which is done in the 12 seconds. So the average speed is actually 5, much larger than the average velocity. And that's because the particle spent some time going backwards from 10 to 12 seconds. Okay? All right, last example. A particle travels back and forth along the x-axis in the following way. 0 to 2, it moves in the positive direction and covers a distance of 25. And then from 2 to 4, it moves in the positive direction some more and covers a distance of 50. So where's the back and forth part, right? It's just going forth without the back. We'll get to the back in part C. But definitely we see that it's 25 positive and 50 positive. Okay? Okay, so, you know, kind of straightforward interpretation there. It sounds a lot like the dragster, doesn't it? Right? You know, kind of at first it was moving more slowly and then it sped up. Well, let's find out. Average velocity then would just be the total displacement over the total last time, 19. That's average speed, excuse me. All right, and that's because this is actually the total distance, and then velocity is a displacement, which is the same as the total distance. Again, unlike example 2, because there was no backwards. But in part C, I do ask, how far and in what direction would the particle need to travel in the subsequent second after t equals 4 seconds in order for the average velocity to be 0? Well, for the average velocity to be 0, we need delta x to be 0. We need x final to equal x initial. And the only way for that to happen is for the particle to get back to where it started. Well, it started at 0, went 25, went another 50 for a total of 75. So that means it's got to go, negative 75. It would have to go negative 75 in the final second, which would be a final velocity of negative 75 meters per second because it's doing it in 1 second, although I didn't ask for the velocity. Okay? So that would give you an average velocity of 0. Would it give you an average speed of 0? Definitely not. All right, and I'll let you think about that. Okay, so are these examples really straightforward? I sure hope they are. They're meant to be. They're meant to lay a foundation without complicated problems, but establishing a firm understanding of exactly what velocity is, because we certainly need that as we move forward. And you've got a couple of problems that you can do for further practice. I left some here for you, all right, of 2 of the 3 types. All right, I didn't give you a type problem for the motion diagram because I don't focus on motion diagrams in this class. All right, they're definitely kind of a side note that we'll address, but move on to other things. Well, thank you so much for watching Lecture 3, covering the first 2 sections of Chapter 2, and please look out for more videos covering Chapter 2.